All right, thanks so much. Good afternoon, everyone. Again, my name is Nick Ginner. Happy to have you here from wherever you're attending from. And so thanks again for attending this Esri National Government Technical Workshop Series presentation on analysis in ArcGIS Pro. My name is Nick Ginner. I work in Esri's Educational Services team as a technical lead, and my job is to provide expertise on spatial analysis and remote sensing for all of our instructor-led and online training. So in the next hour, we're going to cover one of the most important and powerful capabilities of GIS, analysis. And we're going to actually do this using a real world example to actually do some analysis to solve a spatial problem. And that spatial problem is going to be, where is the best location for a new fitness center? Now, we might choose a fitness center, but in truth, it doesn't matter what the actual type of facility is. It's just about location analytics. So a brief agenda, we'll first define what analysis is, and then we're going to look at analysis in terms of sort of the dimensionality of data. In ArcGIS Pro, we could do analysis in several dimensions, including traditional 2D, the spatial dimension. We can add in the third dimension, some things like elevation or depth or height. We can even bring in the fourth dimension, time. So we'll talk about how to do analysis in these few different dimensions. And we're going to organize this presentation similar to how the analysis tools are organized in the software. Things like proximity and overlay and raster analysis and network analysis, etc. We're also going to spend some time discussing charting and how the use of traditional non-spatial charts, like bar charts and line graphs, alongside spatial analysis techniques can really enhance your analysis experience. As we come down the home stretch, we'll talk about some ways to automate analysis with ModelBuilder and Python, and then we'll talk about some ways to extend analysis beyond the techniques that ship with the software using Python and R. So a lot to cover, but a lot of good stuff. So at the most basic level, what is analysis? Well, I like to think of it as basically something that turns raw data into information or knowledge. And when we add the spatial to this, it turns raw spatial data or geographic data into information or knowledge. And now geoprocessing is the rich suite of tools and a framework for processing geographic data in ArcGIS Pro. At the most current version of ArcGIS Pro, which is version 2.5, there's somewhere on the order of 1,500 total geoprocessing tools. They kind of fall into three categories: data management, data conversion, and analysis. We're going to focus mainly on the analysis ones, but at the most recent version of Pro, there's about 80 new geoprocessing tools. And analysis is achieved in ArcGIS Pro mainly using these tools. Okay. However, there are several wizard-type workflows for specific types of analysis that we'll talk about. These include network analysis, performing geostatistics, as well as business analysis. So let's start with the most fundamental types of analysis: proximity and overlay tools. These tools help you answer questions like, what is nearby or close? What things are within other things? And where do things tend to overlap? So these tools fall in the analysis toolbox, and they do things like feature extraction, clipping, proximity and overlay analysis, intersects, union, spatial joins, your standard buffers, summarization, summary statistics, etc. So an example here might be a company has store locations, and what they've done is they've created 1, 3, and 5 mile rings around each store using buffer. What they could then do is overlay their customer data and perhaps calculate the average dollar spent within each one of those rings and generate some summary statistics based on where their customers are coming from. Basic stuff combining proximity and overlay. A new tool at version 2.5 of Pro is one called Count Overlapping Features. This is one that, let's say, for example, you have, say, school locations here in these Massachusetts towns. You create maybe a 1 or 2 mile buffer around each school location. And what Count Overlapping does is it allows you to quantify and look kind of where the density is, the most dense areas of overlap amongst all of those buffer polygons. Some general proximity and overlay tools. Raster analysis. Now, raster analysis involves many of the similar proximity and overlay concepts, except with raster rather than vector data. These tools exist in the Spatial Analyst toolbox and require the Spatial Analyst extension. And they're mainly for doing things like spatial modeling and analysis using raster data. Things like density analysis and all sorts of distance type raster surfaces. You have some deterministic interpolators, and you could do traditional map algebra, suitability modeling, and create different surfaces. So an example of raster analysis would be suitability modeling. Where's the best location for a new vineyard, perhaps? And we know that vineyards, in order to grow grapes, require certain elevation criteria and certain sun angles. And grapes grow better on certain slopes, and they grow better where there's better solar radiation. And we want to put vineyards close to roads so products can be shipped in and out. And so when you combine all of these different variables and how suitable they are for growing grapes, combine those into one surface where you can identify, say, the best locations for a vineyard. With raster analysis, you can also do things like delineate watersheds based on digital elevation models and do classic density maps. So let's take a look at our first demo. We'll set up the scenario and the certain questions that we want to answer. So again, our goal of this is to find the best location for a new fitness center or gym. And so we're going to need to answer questions like, where are our current gyms located? Where do our current gym members live? Which gym is each member closest to? And where are the highest concentrations of gym members? And we'll do this using proximity and raster tools. So let's take a look at our data. We're located here on the eastern portion of Massachusetts and a little bit into New Hampshire, so basically the Boston suburbs. And what we have here are 10 locations of current gyms. Again, our end goal is to try to find the best location for a new gym. So currently, we have our customers mapped. There's about 1,800 customers, and their color identifies which gym they're associated with. And we could visualize this in another way. So we could tell here immediately that some of our customers that are closest to the Boston location are actually traveling further to the Boston location than they are to perhaps the most near gyms, okay? So this is just immediate information that we could figure out. But we want to get a better visualization of this idea of nearness. So we're going to start off by running a tool called Thiessen Polygons. So I'm going to go to the Analysis tab and go to Tools, and under Analysis Tools, under Proximity, we're going to create Thiessen Polygons. And what these do is they're going to give us some indication of which area is closest to each gym rather than any other gym. So our inputs here will be the Boston gyms. We'll call these Thiessen. And we're going to use an environment setting here to maintain that our processing extent is the extent of our gym members. And we'll click Run. So what this immediately does is create this set of polygons such that all area within each polygon is closest to the gym within it than to any other gym. So again, if we go to the Boston example, we can immediately see here that this particular polygon in the center here, it's actually closest to the Boston gym location, but it's pulling customers from many other locations. So we might need to think about sort of reallocating these different areas for our gyms. Let's now take a better look at the concentration of our customers. All right, so I'm going to turn off the lines, and we'll turn on our member locations. And the first thing I'll do is go to the Appearance tab, and under Symbology, I'm going to choose to make a, I'm going to choose to make a heat map. And this is just going to give me a sense of how dense the distribution of my customers are. And so we can see here that the sparser distribution or sparser visualization of customers is kind of in the New Hampshire area in the outer suburbs. And there's a much denser distribution of the customers around the Boston location. Now, one kind of cool tip with regard to visualizing this data as a heat map, right now this is smart mapping, okay? So as I zoom in, that service is gonna change on the fly. But if I actually wanted to create a raster here, under Symbology, I can go up to the little burger button, and I have the option here to convert to a static raster. So when choosing this, this will immediately open up the kernel density tool. And again, running kernel density, this will give us a visualization of the concentration of these gym members. So I've already run one of these, and so let's take a look at this here. Turn on our kernel density surface. Again, we get a good visualization of the distribution of our customers, mainly around the Boston gym location, some around the, specifically around gym number 8 and gym number 5, where there's a higher concentration. So what have we learned? With just a few proximity and raster tools, we now know kind of the extent of our customers. They run, or they come from basically the Worcester area down to the Cape, all the way up into New Hampshire, where the highest concentrations are in Boston and the surrounding suburbs. We also learned that many of our gym members actually travel further than their closest gym, and really the New Hampshire gym doesn't have that many customers. So it's a great start, and we'll continue building this analysis from here. All right, so back to our slides. Let's talk about network analysis. Network analysis requires a network analyst extension, and what it does is it provides tools for working with transportation networks. These include techniques such as calculating service areas, doing routing, location allocation, vehicle routing problem. So an example of service areas, these rings represent, say, 5, 10, and 15-minute drive times from specific facilities. You can do routing, calculating the best route from an origin to a destination. You can use, or you can solve the location allocation problem, which essentially allows you to locate facilities to most efficiently supply demand points. You can calculate origin destination cost matrix, which essentially calculates the least cost paths from origins to destinations. Do the vehicle routing problem, routing for a fleet of vehicles, and even think about doing 3D routing, right? So imagine how useful it can be for, say, a fire company to know the most efficient route from the entrance of a building to, say, an apartment on the 5th or 6th floor. So let's go back to our study, and we'll look at network analysis and another type of proximity and overlay analysis. All right, so we're back in our Boston study area, and what we're going to do now is calculate some drive times to get a sense of each gym's study area. So I'm going to click on my Boston gyms, and from the Analysis tab, I'm going to click Network Analysis, and I'm going to click to generate a service area. And what this is going to do is to make a service area layer. And again, the idea is to get a sense of what spatially a 15 or 20 or 25-minute drive time looks like from each gym. So this is going to open up the service area tab. And the first thing I'll do is import my facilities. So I need to basically tell the layer what the input locations are. And those input locations are my gym locations. So I'll say run. The next option here is to specify some parameters. So I'm interested in a drive time. I'm interested in a drive time to my facilities. And I'm interested in a, say, 15 and 25-minute drive time to each one of the gyms because, you know, people don't want to drive that far to get to their closest gym. So we'll specify these parameters and we'll run it. All right, so we see here the pink area in the middle represents a 15-minute drive. The darker pink area around it represents a 25-minute drive. So if we turn on our customers, or I should say our gym members, we immediately see that there are definitely gaps where we have gym members coming to gyms that are outside of these service areas that we're interested in. So we're going to try to do something about that. So here's another version of that map we just made. And what we really want to learn is we want to learn about the demographic and lifestyle characteristics of the people that live within these 15-minute drive times of our gyms. These are going to be our ideal customers. We want to know, do they like to go to the gym? We want to know what their income is like, what their lifestyle is like. Do they work out from home or do they like to go to the gym? So we need to identify our ideal customers. And to do this, we're going to use a tool called Enrich. And so what Enrich does is it takes advantage of Esri's curated demographics data and basically allows you to choose from something like 13,000 demographic, lifestyle, consumer variables to append to your data. So if I click on one of my drive times here, you'll note here that my attributes do not contain any sort of socioeconomic or demographic information. And that's why, from analysis, I want to choose to enrich my data. Now, what I'm going to actually do is go into my history here and show you how I've run Enrich and what I've basically added in. So again, I'm looking for my ideal customer. So to each one of these yellow polygons, I want to understand what the median household income demographics look like, the number of people that exercise at clubs 2 times a week, and then the total population in certain tapestry groups. Tapestry is basically a market segmentation categorization that identifies geographic areas, lifestyle characteristics. So basically what I'm doing is I'm using Enrich to add these variables into my drive time areas to get an understanding of the people in those areas. So in the interest of time, I'm not going to run this, but basically what you end up with is the same output. Yet when I click on each one of these drive times, I now know the median household income, the number of people that go to the gym, as well as the number of people that exist in these different lifestyle tapestry groups. So I have this information that I could use about my customer base in additional analysis. All right, so we have that. Now let's go back in and we'll turn on our 15 and 25-minute drive times. We'll turn on our current gym members. And what we now want to do is to get a sense of how many of these gym members are existing outside of these ideal service areas. So we'll do a simple select layer by location, where I'm going to select my gym members that intersect with the 15 and 25-minute drive times. And I'm actually going to choose here to invert the spatial relationship because I actually want to select the ones outside of these areas. So now anything in pink is essentially gym members that are sort of in underserved areas. Okay, so we're going to keep this in mind as we then proceed with this analysis and figure out where the best place is for a new gym. All right, so let's go back to Pro, or to PowerPoint, I should say. All right, so we've talked about proximity and overlay. We've talked a little bit about raster. We've talked a little bit about network analysis. Now let's start to talk about some of the statistical tools that are available in ArcGIS Pro. First one being geostatistics. And this requires the Geostatistical Analyst extension. And these are tools for performing both deterministic and geostatistical interpolation. It provides options for doing exploratory spatial data analysis, kriging methods, doing things like sampling and simulations, doing interpolation in 3D, and it provides a geostatistical wizard, which is this sort of interactive wizard that walks you through the process to model the structure of spatial data, which is what you need to do kriging. So an example of performing geostatistics is to take discrete measurements of some continuous data like temperature. Important part of geostatistics is to do exploratory spatial data analysis. There are many assumptions associated with methods such as kriging, and these assumptions need to be met in order to provide optimal predictions. Some of which include that your data is normally distributed. So there's tools to look at histograms and QQ plots, which give you a sense of whether your data meets certain assumptions. The big kind of, the most important part of the geostatistical wizard, or one of the most, is the semivariogram, which allows you to model the spatial structure in your data, and it informs the parameters used to make the prediction in kriging. So what you could then do with geostatistics is take those discrete point measurements of a continuous variable such as temperature, create a prediction map, and not only a prediction map, but also a standard error map. And these maps give you a sense of how good or how reliable your predictions are. Staying in the theme of statistical, we have many spatial statistics tools, and these tools in the spatial statistics toolbox are available at all license levels in the software. These are going to be tools for performing spatial statistics, descriptive spatial statistics, and inferential spatial statistics, which are tools for determining if spatial patterns are significantly different from random. There's also tools for performing prediction. And these prediction tools can be essentially traditional ordinary least squares regression techniques, but also some different geographic regression techniques and machine learning methods. So for example, of a descriptive statistical tool, here's one called standard deviational ellipses, which gives you a sense of directionality and concentration of a point pattern. Tools like hotspot analysis and cluster and outlier analysis, finding hotspots, cold spots in your data. Also doing things like multivariate clustering, so finding clusters in data based on their attributes, and the ability to do this in a spatially constrained way. So in this example, every single one of these polygons in yellow is more similar in terms of its attributes to all the other polygons in yellow than to any polygons in any other color. So different clustering techniques. Again, different regression techniques, both traditional, non-spatial, as well as geographically weighted regression. So in this case, what you're seeing here is that this is the result of a geographically weighted regression, and that the darker counties here in the US have a stronger relationship between the dependent and independent variables than do the lighter counties. And some of our more recent tools for, again, understanding how relationships between data variables actually vary across geographic space. So lots of really great spatial statistics tools. We also have many tools that then incorporate that fourth dimension, time. And these tools build upon some of the spatial statistical methods by incorporating that temporal dimension. Are there patterns in both space and time? And these are available in the space-time pattern mining toolbox. Again, they perform spatio-temporal statistics, things like emerging hotspot analysis, time series clustering, and then being able to view these results in both 2D and 3D. So here's an example of tornado locations in the state of Texas. Of course, it's important to visualize temporal data in something simple like a line graph, right? We can see here Perhaps that there's a trend, right? Tornadoes have maybe increased from 1950, maybe stabilized a bit, and then kind of dropped again towards the beginning of the 21st century. But we can incorporate this temporal element into the spatial analysis. So this is a result of something called emerging hotspot analysis. So it builds upon the traditional spatial cluster analysis technique, hotspot analysis, and helps you determine if the hotspots and cold spots that you see are new or are kind of fluctuate over time or are on the decline by incorporating time. You can also visualize the results of these temporal hotspot analyses using space-time cube visualization. So you're essentially seeing a stack of these locations over time, and the results of that analysis over that time. We also have time series clustering, which essentially it creates groups of locations in your data that have a similar time series. All right, let's get back to solving our problem. And we're gonna actually see how a few spatial statistics tools help us identify some of those ideal locations for our new gyms. The questions we're answering here is, where are the gym members most densely clustered? Where is the center of each cluster of members, in particular, these sort of members that are underserved by the drive time areas? And then finally, we'll start to hone in on which potential gym location is most similar to the best performing existing gym. And this might be the one that we decide to choose as our new gym going forward. All right, so we'll go back to ArcGIS Pro. And I have to clean up a little bit here. So I'm gonna turn off my drive times. And again, remember, I have selected customers, or I should say selected gym members that are outside of those drive times, so the underserved ones. And what we want to do is to essentially go in and find clusters of points based solely on their location and try to sort of separate these clusters from noise. So I'm going to go back into analysis and go back into tools. And we're actually going to hit the spatial statistics toolbox. And again, with spatial statistics tools, simple descriptive statistics of spatial patterns, quantifying patterns, mapping clusters, doing modeling of spatial relationships. In this case, we're going to choose one of our clustering tools called density-based clustering. And again, we're going to look for clusters of points based solely on location and try to separate these out from noise. So my input point features are going to be my gyms, my gym members. And again, this is only going to operate on the selected points. We'll call this gym members density. Density-based clustering has 3 different algorithms available. The one that we're going to choose here is called HDB scan. This is by far the most data-driven approach for density-based clustering. It has the least amount of user input parameters. All I need to tell it here is that the minimum features within each cluster have to be 25 gym members. So let's run this. Note there that I actually didn't specify the number of clusters I wanted. It automatically found 4 clusters of data. So anything that's colored is considered a cluster that met that criteria. Anything that's sort of gray and small is considered to be noise. So I have these 4 customer clusters. What I'm then going to do is a selection. So we'll go to map, we'll go to select by attributes. From these density clusters, I'm actually going to select the ones where the cluster ID is equal to -1. Nope, sorry, is not equal to -1. This should select only those points that are not noise, only those points that are part of clusters. Now with the selection here, I'll actually go back to my spatial statistics tools and grab one of the ones for measuring geographic distributions. This one's going to be called mean center. So what mean center does is it basically finds the average center location amongst a group of features. So my input feature class here will be the gym members density. On the selection, we'll keep it mean center. And the only other thing in here I'm going to specify is a case field, and the case field is cluster ID. So instead of finding one average center for all the data, it's going to find 4 average centers, each one associated with one of the 4 clusters. All right, so if I turn off these, I've now whittled down this area to 4 potential gym locations. And that was based on where my current gym locations are, where their service areas are, where my current customers are, and where the current customers cluster in underserved areas. So we're going to stop here for now with this idea of 4 potential new gym locations. And then the next thing we'll do is whittle those 4 down to only 1. All right, so we're in the same area here. And if you recall, what we did was we had our current 10 gym locations in yellow. We know the information about the people that live within those yellow areas, such as their income, their exercise habits at gyms, as well as their tapestry information, lifestyle characteristics. What I've then done behind the scenes is I've created the same 15-minute drive times around my potential locations, which are in blue. And I've also gone in and enriched those with the same information. So I have this sense of what the customer base is like around my existing gym locations and what the customer base is like around my potential gym locations. And of those 4 potential gym locations, I want to now identify the best one, which is most similar to my best performing gym location. So what I've already done behind the scenes is I've run a tool called Summarize Within. And essentially what this did was for each one of the 15-minute drive times, it gave me a count of the average dollars and total dollars spent by all the members attending this particular gym. So I could say, use the average dollars spent as my indicator of my best performing gym. So here's an example of how the charting capabilities can be helpful in Pro. What I'm going to do is create a chart, a simple bar chart around my existing gyms. And I'm going to create a chart for facility ID. And I'm going to take a look at the average amount of money that facility generated. So I could see here immediately that facility number 5, which is now selected on the map, is my best performing current gym location. So I'm going to keep that selected. And then I'm going to do one more step here to whittle down my 4 potential gym locations to the one that's most similar to my best performing gym. So we'll go back and we'll go back to Spatial Statistics tools one more time, and I'm going to use a tool here called Similarity Search. And we can see here what this tool does is that it identifies which candidate features are most similar or dissimilar to one or more input features based solely on their attributes. All right, so my feature to match is my best performing store. So that's going to be Boston Gyms. Yep. My candidate features will be all of my potential gyms. We'll call this Sim Search. I'm going to choose to find the most similar based on attribute values. And the attribute values that I'm looking at are those same 4 that we enriched with. The median household income, the number of people that exercise at gyms, and then those different tapestry attributes. And again, my number of results is going to be 4 because I have 4 potential gym locations. So let's run this. And this should just complete here in a second. So here's what my output looks like. The darker the polygon of the potential, the most similar it is to my existing best performing gym. So if I were to go in here and turn on my Massachusetts town boundaries, we see here that the potential at the gym with the most potential for, I'm sorry, the potential gym that is most similar or most ideal to what we're looking for exists in the town of Natick, Massachusetts. So we might then hone in and start to find available facilities for this. Okay, so we did a lot there. We essentially started with current gym locations and our customers. We identified where there's gaps in service to those customers. We did a few different spatial statistical methods to kind of whittle down these potential locations to a final one, and we're going to continue on from here. All right, so back to our slides. Where were we here? Okay, let's not forget 3D. In ArcGIS Pro, you could do analysis in 3D, and you could do that through the 3D Analyst extension. These are going to be tools for working with things like digital elevation models, so surface models, or 3D vector data, LiDAR, and multi-patches. You could do things like look for different relationships between 3D features, interpolation, data management, generating surfaces, doing visibility analysis. So things like generating sight lines, using elevation data or 3D vector data, looking at skylines, so basically dropping a point and seeing what might be visible at the top of a skyline. Doing things like calculating volumetric measurements. In this case, you can actually calculate perhaps how much water is in this sort of channel leading up to a dam. We have different 3D tools for generating procedural symbology, as well as doing traditional proximity and overlay, but with 3D. So for example, this is let's say this is a power line. What I've done is created, say, a 15-foot buffer, 3D buffer, which actually is a cylinder around this power line. And I could actually see if trees intersect this 15-foot buffer around a power line. That's a real world problem. And of course, in 3D analysis, you work with LiDAR data in Pro as well. GeoAnalytics Desktop tools. These are tools available at the advanced license level. And what they allow you to do is to perform kind of traditional geoprocessing type things like analyzing patterns and summarizing data and proximity like we've already seen, but on bigger data sets. So you do this by sort of leveraging parallel processing over multiple cores using Apache Spark, but it's all on the desktop. So an example here is this example I did where I mapped 1.8 million wildfire incidents in the US. And what I wanted to do is to get a count of wildfire incidents per state. So using the traditional summarize within tool, so not GeoAnalytics Desktop, this aggregation of 1.8 million records to 50 states took almost 5 minutes. Using the same tool, but with GeoAnalytics Desktop, this aggregation took only 29 seconds. That's about a 10 times difference. Okay, so doing these sort of traditional GIS type of analyses, but with distributing the processing over multiple cores. You can also do imagery analysis. So we've already kind of discussed raster analysis using the Spatial Analyst extension. But there's also a suite of tools for working with imagery and remotely sensed data. We have tools for working with and doing deep learning, stereo mapping, image classification, so traditional remote sensing image classification using statistical techniques as well as machine learning techniques, image space analysis, working with video and doing multidimensional analysis. So here's an example of traditional image classification. You take an image and you can either do pixel-based or object-based classification. You turn that into categories using different algorithms. We also have the ability to work with, we'll refer to it as map space versus image space. So this is an example of an image that was taken at an oblique angle. If you look at it top side down, you're basically seeing that these buildings look kind of bent, and that's due to the angle. But we can actually visualize and do analysis in image space, which allows you to basically view that imagery from the oblique angle that it was taken. We also have a bunch of tools for doing multidimensional analysis. So basically working with scientific data cubes like NetCDF data that contain many variables, geophysical, environmental, climatological, depth, time, etc. And these all fall under imagery analysis. Charts. Let's not forget charts. Let's not forget the non-spatial. We spent most of our time thus far focusing on spatial analysis tools. And we'd really be remiss not to consider how important these traditional non-spatial charts and graphs are in analysis. And particularly when these graphs and charts are used side by side with spatial analysis tools. I think as GIS folks, we tend to think, as GIS folks, we tend to think that a lot of traditional data analysis, people focus on charts and graphs and line charts and neglect the spatial. As GIS people, I tend to think that sometimes we focus too much on the spatial and neglect the traditional non-spatial. And I think that charts really have a big impact on what we could do. And so they help us visualize qualitative, quantitative, and temporal data. And there's some great charting capabilities in Pro. You could do things like create traditional bar charts. We just saw how looking at a bar chart of our dollars generated for each of our gym locations, how that helped us see the best performing one, and we could interactively select it. It selects something on the map, everything works together. So doing things like bar charts, box plots, which kind of give you this combination of categorical or qualitative and quantitative, traditional line charts, which are great for looking at time series. Other ways to visualize temporal data, such as data clocks and calendar heat charts. Again, traditional histograms. We just saw how important understanding a distribution of your data is for things like geostatistics and meeting different assumptions, QQ plots, again, with normal distributions, as well as the ability to create scatter plots, so bivariate and even scatter plots on a matrix for a number of different variables. So great charting capabilities, not only for the kind of pre-analysis exploration of data, but a lot of the geoprocessing tools, specifically a lot of the geospatial statistics tools, actually produce charts along with the mapped outputs, which can be really helpful for interpretation of results. And I think we already saw that a little bit with the time series clustering. All right, so we also have a bunch of ready-to-use tools and portal analysis tools. And so these ready-to-use service tools, they perform a lot of the same types of functionality as the geoprocessing tools we've already looked at. However, they leverage their services, right? So they leverage ArcGIS Online's analysis capabilities. The portal analysis tools kind of do the same thing. However, they rely on an ArcGIS Enterprise deployment. So again, a couple of the ready-to-use tools mainly deal with network analysis because ArcGIS Online provides a network data set as a service to do a lot of this. But there's also ready-to-use tools for doing some more of those raster type analytics. Again, portal analysis tools, both with feature analysis and raster analysis. Particularly raster analysis, they require ArcGIS Enterprise with image server. And basically it allows you to leverage distributed server-based processing for rasters and imagery. So again, a lot of the similar tools for pattern analysis and summarizing data. Raster analysis tools, a lot of the similar ones, but again, being able to do it distributed. And then GeoAnalytics tools that require GeoAnalytics server, but again, server-based processing. Primarily the raster analysis and GeoAnalytics tools are for working with big data, in quotes. All right, as we come down the home stretch here, we'll talk about automating analysis. So thus far, everything we've done is to run individual tools. But what if we want to run tools over and over again on the same data? Maybe we have a folder full of 100 shapefiles and we want to reproject all of them into a different coordinate system. Well, I could run the project tool 100 different times, or I can automate it, perhaps through ModelBuilder or through Python, and get that done all in one click. Or maybe I want to connect several tools together in a workflow that could be repeated. So a couple of different ways to do automated analysis are through batch geoprocessing, through ModelBuilder, exporting to a Python script. And then one of the latest things is to be able to actually schedule geoprocessing, where you can go into a tool and you could schedule it to run at a certain time each day or at a specified time, maybe when your computer isn't doing other really computationally intensive stuff. So an example of batch geoprocessing, here I have 8 land cover maps for 8 different towns in Massachusetts. And for any geoprocessing tool, if you click on it in the toolbox and right click on it, you have the ability to do that tool in batch mode. So in this case, I'm running a tool called Tabulate Area, which calculates the area of different categories within polygons. And so the batch version of it is going to take in 8 raster inputs. It's going to take in the polygons of the towns, and what it's going to do is run 8 tabulate areas, 1 on each town, with basically 1 mouse click. I can also use ModelBuilder, which allows me to string tools together. The 3 geoprocessing tools here, XY table to point, near, and XY to line, all of these combine to create a spider diagram. And so once I create a model, I can do a little bit of work with parameters, all in the interface to create a geoprocessing tool that actually looks like it ships with the software, with the graphical user interface. So you could do that with ModelBuilder. You can also export models directly as Python files if you have to do further work with, or maybe you have to use some kind of non-GIS Python type workflows. What that'll look like here is this script right here is script that was generated automatically just by clicking this export to Python file, right? So I didn't write any of this code. It's all in there. It's all done for me. And not only is this helpful if you have sort of non-GIS Python workflows, but it's really helpful if you're kind of a new person to Python, because this, I think, can help you learn what the syntax looks like and can help you kind of troubleshoot and get you on your way. It kind of gives you this baseline. All right, so a couple more things. We talked about at the beginning a little bit how we're going to discuss extending analysis with Python. And so at Pro 2.5, you can now leverage the interactive analysis capabilities of the Jupyter Notebook directly in the ArcGIS Pro application. And this allows you to tie a lot of things together. Core Python functionality, ArcPy, so all the geoprocessing tools, the ArcGIS API for Python, and perhaps most importantly, hundreds of third-party Python libraries to do things like data cleaning, data engineering, machine learning, statistical modeling, and so on and so forth. So let's go back to our study area here, and let's kind of review what we did. We have our original 10 gym locations. And what we did was we decided that the best place for a new gym is where this green dot is in Natick. What we then did in the beginning was showed you where all of the original customers are coming from, right? And remember, we saw that a lot of these customers, or I should say gym members, are attending the Boston gym location, but they're coming from far away. So given that we've added a new gym, we're going to essentially remove a gym and then reallocate our customers. All right, so we'll turn these off. Again, original gym locations, new gym location. What we've decided to do is to remove the New Hampshire gym location and replace it with our new one. So that's what this looks like here. So we still have 10, however, or I should say we still have 9, however, no longer the New Hampshire gym location. What I've done behind the scenes is I've run a tool called location allocation, which essentially allows me to reallocate my customer locations using basically there's a couple of different methods to do this. I use one called maximize attendance. And what this did was it reallocated all of my gym members to the new stores, or I should say to the existing plus the new gyms, okay? And that's kind of what this looks like. So I took this one step further, and I wanted to use Python, in particular something called a search cursor, to help me calculate the average drive time for all the gym members to the gym that they've been newly allocated to. And while I don't have enough time to really go through this, I'll show you at least how the notebook looks. So the first thing I have here is to import a few different modules. I've defined a couple of variables. So my origins are my new gym locations, and my destinations are my reallocated customers. And essentially what this step is doing is it's using something called a search cursor to loop through each gym location and its newly assigned member and use a network analysis tool called closest facility to calculate the drive time for each member to the new gym that it's been assigned to. It then goes through a series of steps to average the drive times and aggregate each gym location for display. So for example, if we go back to our map here, these are the newly aggregated Boston gym locations and customers. And for my final map, based on the Python script, what each one of these dots is showing is the average drive time for each one of the customers. Right, so we've taken a lot of data and kind of whittled it down through a series of steps here. And again, if you look at the map, this kind of makes sense, right? You have a lot of the New Hampshire customers that were formerly going to the gym, the most northern gym, now having to come to this one in Massachusetts, and they have a longer average drive time. We've definitely whittled down the distance that customers are coming to the Boston location. And not only have we sort of whittled it down, but we now have a better sense of what the average drive time is for all those customers, gym members. So all in all, for this analysis, we started with a set of gym locations and a set of members assigned to those locations. And we looked at the data and we got a sense of the distribution, and we determined the best potential locations, and we used a couple of different methods to kind of whittle down to the best location based on our best performing current location. We reallocated our customers, and we used Python to kind of do some calculations for us to get the average drive times for our new gyms. Okay, so last thing I want to cover here before I wrap up and to continue the conversation of extending analysis, we'll talk a little bit very briefly about R. So another great way to extend the analysis capabilities of Pro is using something called the R ArcGIS Bridge. And this allows you to combine the statistical and data science capabilities of the R programming language with the spatial data management, visualization, and analytics of ArcGIS. So there's kind of three main patterns of use here. The R Bridge can be used by ArcGIS people to access thousands of open source statistical packages in R and apply them to their spatial data. It can be used by R users to access the spatial data storage, visualization, and spatial analysis capabilities of ArcGIS. And it can be used by ArcGIS developers to basically create custom geoprocessing tools that leverage R functionality. So let me show you one quick brief example of how you can use R with ArcGIS. What we're looking at here is a map of, the use case here is species distribution modeling. So we're looking at a map of incident locations of the three-toed sloth in the northern part of South America. So what I have are incident locations designated by these crosses, and I have a series of environmental variables representing things like temperature, precipitation, different wetness measures, so several different environmental sort of continuous variables. And then I also have a map here on different biomes. So the idea here is that we have known occurrences of the three-toed sloth. We have a bunch of environmental variables. We want to create a suitability map that might help us figure out where the best locations are for, or I should say, where these species will be distributed. So very briefly, what I've done is I've created an R script, and of course, I'm not going to get into this, but there's a few main things to be aware of with regards to linking together ArcGIS and R. The first is the ArcGIS binding library. This is the library that's required to essentially make the connection between ArcGIS and R. It checks that it works. And then there's a few lines of code here that basically take a feature class from an ArcGIS geodatabase and turn it into a format that can be used in R. So this creates an R data frame. I read in my rasters, and truly the most important thing are these few lines of code to read in the ArcGIS data. And then everything else that I do here is very R specific. So this is where I can actually use different species distribution modeling tools, like this one called BioClimb, as well as another one called MaxEnt, to actually do species distribution modeling. These are the capabilities that are not available in ArcGIS. But the point is that I was able to very easily read in ArcGIS data, do a bunch of stuff in R, and then finally write the data back out as a TIFF that I could read in ArcGIS. So very simple with a few lines to read data in. All the stuff in the middle is R capability, and then a few lines to write things back out. So what that eventually created here were two examples. Here's the BioClimb suitability and the MaxEnt suitability, where green is more suitable for the three-toed sloth. So again, we don't have much time to go into the details, but the point is very simply, you can take your ArcGIS data, export it into a format that you could read into R, do your statistical work, your machine learning work, your modeling in R on capabilities that are not in ArcGIS, write it back out, and then use more tools in ArcGIS or visualization or whatever you need to do. So there's a couple of examples of extending analysis. And I'm coming up right on the final minute here. So thank you for coming. I know it was a lot of information, but hopefully that gives you a good indication of pretty much all the different analysis capabilities in ArcGIS. Again, tons and tons of tools, but the most important thing is that you start off with a good spatial question and figure out the best ways to answer that question, and there's certainly many of them to do so. So hopefully it was helpful, hopefully you enjoyed it, and stay well. Thanks.